Good evening, students. In last lecture we have seen what is electric potential and potential due to point charge. Today we'll see the relationship between electric potential and electric potential difference and electric field intensity. Okay, so we'll see the difference, relationship between electric potential difference and electric field intensity. By definition we know that the potential difference will be equal to, let's say, VB minus VA, where VB is potential at B point, VA is potential at A point. That will be equal to the work done in bringing positive charge from B to A divided by the magnitude of the charge, and this will be equal to the force on unit charge into dr on unit charge into dr. From this we can write dV equal to minus E into dr. Here the force on unit charge, and that will be QE. This will be equal to QE. The Q is 1, then it will be equal to 1 into E, and it will be equal to E. Okay, from here we can write this E dot dr. This is the dr from here. The same formula. We can write the same formula in vector form. That will be dV equal to E dot dr. So the potential at any point E equal to minus integration of E dot dr. So this is equation 1. So this is a relationship between electric potential difference V and electric field intensity E at a given point. Next we'll find out what is electric potential due to a point charge. Electric potential we all know F is equal to KQ upon R or X square, where we are talking about on a point charge, a unit point charge. So it will be KQQ small q upon X square, and this will be equal to KQ upon X square if the Q will be plus 1 coulomb. Okay, so from here we will get E equal to F upon Q, and that is F upon 1, that is F, that is KQ upon, so E vector will be equal to KQ upon X square into XK. From the equation 1, the V will come equal to the potential difference, or the potential at a point will be coming as minus integration E dot dr. We put the value of dr, or it can be E dot dx as well. Putting the value, the integration from infinity to r. Okay, the potential at point r. Okay, so when we do the integration and put the value, we get minus infinity to r. So the V will come as integration minus infinity to r kq upon x square dx. kq is constant here, integration infinity to r x raised to the power minus 2 dx. So it will come v equal to minus kq, my apologies, minus kq multiplied by x to the power n plus 1 upon n plus 1. So x raised to the power minus 2 plus 1 upon minus 2 plus 1. The limit is infinity to r. Minus kq raised to the power minus 1 upon minus 1 infinity to r. One upon x infinity to r, kq upon r. So we are getting v at a point r is kq upon r. We'll do a question about using this formula. The question is capital Q is 10 microcoulomb. We have to find out potential. Okay, 10 microcoulomb charge is placed at a point. Find out potential at a distance of 1 meter from the charge. The solution is use the formula V equal to potential equal to kq upon r. The key is we are aware of 9 into 10 to the power 9. Q is given 10 microcoulomb, 10 into 10 to the power minus 6 coulomb. R is 1 meter. So the answer will come 9 into 10 to the power 4 volt. Next we have potential due to system of charge. Potential at any given point due to a system of charges. Let's say we have a system, okay, the charge Q1, Q2, Q3, Qn, and we have to find out potential due to these system of charges at point P. The difference between P and Q is P and Q1 is R1, P and Q2 is R2, P and Q3 is R3, P and Qn is Rn. So potential at P point due to Q1 charge is P1 equal to K Q1 upon R1 P. P2 equal to K Q2 upon R1 R2P, and Pn equal to K Qn upon R NP. So the net potential will be equal to V, and that will be equal to the vector sum of all the potential V1 plus V2 plus V3 plus Vn. Okay, for example, we'll do a question on the same. Let's see, we have Q1 charge, we have Q2 charge, we have Q3 charge. Q1 equal to 1.5 microcoulomb, Q2 equal to minus 2 microcoulomb, Q3 equal to 4 microcoulomb. And due to this charge, the system of these three charges, we need to find out potential at point O. The length of point O from Q1 is 1 meter, Q2 is 2 meter, Q3 is again 2 meter. So what would be the net potential? The net potential at point O is V naught. Let's say it will be equal to V1 plus V2 plus V3, and that is K into Q1, that is 1.5 into 10 to the power minus 6 upon R. Okay, R1, and because of 2 is K into 2 into 10 to the power minus 6. The minus sign will come because it is a negative charge upon R. The third one is the same, K into 4 into 10 to the power minus 6 upon 2, the distance KQ upon R. The final will come, the K will be common, 1.1056 minus 1 plus 2 and 10 to the power into 10 to the power minus 6, that is also will come common. So we'll get the answer. Potential at point 0 because of these three charges, 2.25 into 10 to the power 4 volt. Next we have electric potential due to hollow charge sphere. Electric potential due to hollow charge sphere. Let's say we have a hollow charge sphere. This is a sphere. The radius of this sphere is given R, capital. We have to find the potential at given point P, okay, outside this sphere, and the distance between the center of the sphere and the point P is small r. Okay, so first we'll find out the potential outside the sphere, outside the sphere. So that is R, small r is greater than capital R. What would be E at P? E at P. First we'll find out this. The E at P is E equal to KQ upon R square into R cap. This is equation 1. So the electric potential at P will be equal to V equal to integration infinity to R E dot dr. This will come to minus integration infinity to R KQ upon R square R cap dr. So we'll get over here is minus KQ integration infinity to R s to the power minus 2 dr. That will come to KQ by R. So outside the sphere, the potential V R will be directly proportional to 1 upon R or inversely proportional to R. On the surface, we'll find out B on the B on the surface of sphere, where small r equal to capital R, then BR will be equal to Bs equal to KQ upon capital R, and this is the maximum potential due to the sphere. This is max. Next we have inside the sphere. Inside the sphere, where R is less than capital R. Inside the sphere, we all know enclosed charge is 0. So the electric field is 0 inside the sphere. So the potential V will be equal to integration minus integration infinity to R E dot dr. That will also integration of constant will be equal to integration of 0 will be equal to constant. My apologies, the integration of 0 will be equal to constant. So we will get v inside equal to constant, and that will be equal to v surface, that is kq upon capital R. So no work will be done in moving charge inside the shell. The graph between v and R will come like this. This is R, this is v. Graph will come like this. It will be constant till small r equal to capital R, and after that the VR is inversely proportional to 1 upon R. So graph will be this will be the relationship between electric potential due to hollow charge sphere inside the sphere, outside the sphere, and at the surface. This hollow charge sphere can be conducting and not conducting also. This hollow charge sphere can be conducting or non-conducting. This is also true for solid conducting sphere or solid conducting sphere. Why? Because solid conducting sphere, the charge will remain always on the surface of a conductor. Okay, so if it is a solid conducting sphere, then the charge will be on sphere on the surface, on the outside surface of the sphere. If it is conducting hollow, non-conducting hollow, both the charge will be on the surface itself. Okay, so this is the derivation and this is the relationship for the same. In next class, we will continue with electric potential due to electric dipole, electric potential at point P of the dipole, and on the bisector of dipole. Then we will study about capacitance and capacitor. Thank you.